Okay, so here we go again. I tried to record this twice and my computer crashed both times. So I'm going to kind of rush through this first part because we've actually already covered it. So we're going to cover electrochemistry. I'll probably do this in 2 or 3 parts, 2 parts probably, but here we go. Okay, so we already know about oxidation and reduction reactions. We know that oxidation is the loss of electrons, reduction is the gain of electrons. We use oil rig as kind of the mnemonic to remember that. Oil is oxidation is loss, reduction is gain. These two things have to happen together. So when I have a reaction and I lose 2 electrons, so zinc 0, it's 0 because it's in an elemental state. So zinc 0 converts to zinc 2 plus aqueous. Okay, it can be an ion. It can be 2 plus when it's in ionic form because it's with something else usually. So it goes from 0 to +2. I'm positive I lost an electron. It becomes more positive when it loses electrons. So it lost 2 electrons. Those electrons have to go somewhere. They're not just allowed to remain nowhere. They can't just stay in solution. Okay. So we have something else taking those electrons on. So the hydrogen gains 2 electrons and becomes elemental hydrogen. So oxidation and reduction have to occur together. So loss and a gain have to happen in terms of electrons. That means we have something that's oxidized and something that's reduced, and therefore we have an increase in one and a decrease in another oxidation state. Instead of looking this as a full reaction of both processes together, we can actually split them in half. And there's a couple of reasons that we're going to do this, and I'll show you how to balance these. And actually, it's kind of nice, kind of easy to do. It's a lot of fun to actually get this done. But here's the oxidation half reaction. It involves the zinc species going from 0 to +2 and 2 electrons. So the thing about half reactions is they're allowed to have electrons in them. And this is the reduction half reaction. We have to make sure it's balanced with charge, and we usually use electrons to balance the charge, but we're going to talk about that. But we can break it into half reactions, or both halves, oxidation part and the reduction half. Okay. In order to identify oxidation and reduction, we have to identify oxidation states. And so we've already done this, so hopefully you remember how to do it. There is a set of rules. Group 1, always +1. Group 2, always +2. Group 17, the halogens, -1, higher in the group always gets priority. So fluorine is -1, always. And then if I have fluorine with something like chlorine and bromine, because fluorine is higher in the list, it's going to be -1, and chlorine and bromine would have to change if that's the only thing left. The goal of this is to always identify one thing left, and that's kind of what we're looking at. Oxygen is mostly -2. In fact, it's pretty much always -2, except for when we have peroxides. H2O2 is going to be a -1. And then hydrogen is pretty much mostly +1, unless it's with a metal or unless it's with something else. So those are the set of rules. We're going to list them in order. And when we have one thing left, then that is going to be our oxidation state. So when identifying oxidation states, we have a couple of parts. So first of all, this part above, this is the oxidation state of the individual atoms. So one potassium, or in this case better, one oxygen has a charge of what? Okay, so these are the individual charges of each of these atoms. This down here is the total charge of an atom. So I've divided it into a bunch of categories. So what is the total charge from all of the potassium, all of the hydrogen, all of the sulfur, all of the oxygen? And then over here, I have the charge of the compound itself. The charge here is neutral, and therefore the charge of the compound is going to be 0. So all of these added together have to equal the total charge of the compound, which makes sense. So according to our list, what do we actually know? Well, I know potassium is in group 1, so we know that this is going to have a +1 charge. There's only one potassium, so +1 there. Next up, oxygen is next on the list. I know oxygen is -2 in most cases. There are 4 oxygens at -2 each. So 4 times -2 gives me a -8 total. Hydrogen is the next thing, and it has a +1 charge, and there's only one of them. So now we've gone through everything. We have nothing left. We have just sulfur remaining. So the question is, what does sulfur have to be? And generally what I tell you to do is look at this math. According to this math, what has to go, what does sulfur have to be in order to make that true? Well, sulfur has to be +6 in order to make that true. There's one sulfur. So sulfur has an oxidation state of +6, and we're done. We always do one, the last one is we have to use everything else around it to identify what it actually is. Sorry about Bela barking in the background. She's the worst. It's okay, Bela. I'm joking. She's a wonderful dog, but she's annoying at times. All right. Fe2O3. So again, the whole thing has a 0 charge. It is in fact neutral. What is the charge of the iron? All of the iron together. What is the charge of the oxygen together? And those two things together have to be neutral. So which of those two do I know? Do I know oxygen or do I know iron? Well, we know oxygen is -2, and there are 3 of them, so the total charge is -6. Now we can do the math on this. What does iron have to be in order to make it neutral? Iron has to be +6, and the math is right. And so finally, if there are 2 iron and the total charge has to be +6, an individual iron is going to be +3, okay? All right, last one, and we'll move on. How about NO2 minus? Yeah, just give me one moment. I think I riled her up more. Oh, she's jumping under that now. Anyway, all right, so let's do NO2 minus. So NO2 minus. So we know the whole thing is going to have a -1 charge. Is going to have a -1 charge. We know, again, the individuals. I have to identify oxygen. I have to identify nitrogen. So we know oxygen has a -2 charge, and there are 2 of them, so a -4 altogether. In order to make that math true, nitrogen has to be +3. There's only 1 nitrogen, so it gets a +3 charge. Okay, so hopefully that helps, again, remind you of how that stuff is done. Okay, so oxidation states. Identifying oxidation reduction reactions. We recognize them as the single replacement reactions. And there are many ways that you can actually identify what type of reaction it is. Single replacement is the easiest. If you have 2 metals, and if you have 2 metals, you always check the oxidation states of those. And once you know the oxidation states of those, then it's a matter of saying, all right, well, they've changed, and there we go. We have our redox portion. We have the reduction and oxidation. So we've already done this as well, but let's take a look. So let's assign, based on what we just did, let's assign oxidation states. So cadmium, 0. It's elemental. It's all by itself. So we expect cadmium, because it's neutral, to have a 0 charge. Nickel oxide. I know oxygen is -2. And then if we were doing what we were doing above, that's -4 total. The whole thing is neutral. Nickel has to be +4 in order to make this true. So nickel is going to be +4. Water, again, I would usually just check the metals first. So we did the 2 things that contain the metals. We're going to skip water for now. If I don't have an oxidation and reduction portion, we can go back and check the hydrogen and oxygen there. I know that this is going to be -1 each. Each of the hydroxides is -1 total. Okay. The whole thing is going to be -1. And I guess it's probably better to say it as, all right, this whole thing is -1. The oxygen is -2, making the hydrogen +1. So the 2 of those together give you a -1. So overall, that's -2 though, because there's 2 hydroxides. So cadmium would have to be +2. And right away, we can see cadmium goes from 0 to +2, so it's been oxidized. And then nickel, same thing. Actually, luckily, we're in the same situation. Whole thing is -1, oxygen is -2, hydrogen is +1. Nickel, in this case, is going to be +2. So again, do we have oxidation and reduction? We're going from +4 to +2. So we have a reduction there because it's reducing in its oxidation state, going from, so this is the gain of electrons. So we can deal with number later. And cadmium, going from 0 to +2, this is the loss of electrons. Okay, so we have, so we have a change in the total number of electrons. So identify, what we need to be able to do is identify what is oxidized, what is reduced. Let's start there. So again, oxidation and reduction we are looking at only things on this side. We're only looking at reactants, and we're only looking at things that start the reaction, okay? So oxidized and reduced. The things that are oxidized is cadmium, because it goes from 0 to +2. So cadmium, and that's it. Just the element is the thing that is oxidized. The element cadmium goes from 0 to +2. The element is oxidized. Nickel is reduced. Nickel, the element, is reduced. Good enough. Next, what we're going to look at is the things that are responsible for these actions. So cadmium is oxidized. What is the oxidizing agent then? What is responsible for the oxidation? So if cadmium is oxidized, it can't be cadmium, right? And we also have to find the reducing agent. So if cadmium is oxidized, then that means that it's giving up its electrons. If it's giving up its electrons, it's doing the reducing. So whatever contains cadmium is doing the reducing. The reducing agent is cadmium solid. And so in this case, it's not just the element, it's the entire thing that contains the cadmium. So cadmium solid. And then just like nickel is reduced, it is giving up, it's taking its electrons from the oxidizing agent, which is going to be cadmium. So whatever contains the cadmium. So in this case, or I'm sorry, whatever contains the nickel is the oxidizing agent. I said that backwards, I'm sorry. So the nickel oxide solid is the thing that is responsible for the oxidizing. Okay, so whatever is oxidized contains the thing that is the reducing agent. Whatever is reduced contains the thing that is the oxidizing agent. Does that make sense? I hope so. Okay, so you should be able to do that for pretty much every single thing. Okay, so same question here. Can we identify the oxidation and reduction? So I would ask you to do the same exact thing here. So pause it and give this a go. I'm going to do it right now. Aluminum goes from 0 to +3. Manganese goes from, let's see here, +7 to +4. So I'll do this above. Oxidized, reduced, oxidizing agent, reducing agent. I recognize I'm asking you a different question here, but ultimately we can do this. All right, so the thing that is oxidized, aluminum goes from 0 to +3. So the aluminum is the thing that is oxidized. The manganese goes from +7 to +4. So it's the thing that is reduced in oxidation state. And therefore, if manganese is reduced, it's the whatever contains manganese is the oxidizing agent. Aluminum is oxidized, so it contains the thing that is the reducing agent. So again, so aluminum, manganese, the oxidizing agent is the MnO4 minus aqueous. So that ion is the oxidizing agent. And the thing that contains the aluminum, which is just aluminum solid, happens to be the reducing agent. Okay, that's it. That's how we identify those things. So in terms of half reactions, we don't have to get fancy with the half reactions. We're basically going to write out, so the oxidation half reaction. So aluminum solid to AlOH4 minus aqueous. That's it. We're going to learn how to balance these next, but just start by writing the two components of that contain aluminum in the reactants and the products. So what is the reduction half reaction going to start to look like? The thing that contains the manganese, MnO4 minus aqueous, yields MnO2 solid. And I just finished the thing below, but that's it. So this is how it's going to start. And in fact, we probably should come back and do this one, but maybe I will actually. Yeah. So this is how we're going to start. Okay. So let's talk about the idea of balancing redox reactions. So we have these start to these redox reactions. We want to be able to balance them. So we're going to start with half reactions, how I just did that, how we divided into half reactions. So we have the half reactions. We're going to balance these half reactions individually. So we have two ways that we can do it. We can do it acidic or in a basic method. We will always do this. we will always do acidic, and then we will convert to basic. Okay, so acidic solutions can contain H+, they can contain H3O+, which are the same thing to a chemist, and water. Those three things are allowed in an acidic solution because you're allowed to have those extra protons, right? You're allowed to have that H+ and that H3O+. What you cannot have is what we have in basic solutions, OH- and H2O. You can't have OH- in acidic solution. When you get to organic chemistry, if you ever write OH- in a basic solution, you're wrong, right? Don't include those in acidic solutions. It's just not allowed because it just gets gobbled up by the protons that are present. It makes water. So we're going to have a skeleton reaction, which is going to be kind of the parts that this is a skeleton reaction. Before we start writing anything, those are our skeletons. Okay, so a skeleton reaction, then we are going to add parts of the acid. Then we're going to write out that half reaction, which is going to contain electrons, and then the net reaction when we add them together. So let's take a look. So here I have an unbalanced redox reaction. So let's divide it into the two parts. So which one's oxidized and which one's reduced? Ultimately, it doesn't really matter. We can just ignore what's oxidized and what's reduced. We can actually just say, all right, well, I know that I have VO2 plus aqueous yields VO2 plus aqueous. Yeah, that's it. And is that oxidized or reduced? You can look it up. I don't really care. It's reduced, but. And then manganese MnO4 2 minus aqueous. I'm just going to skip writing the aqueous part because it's going to add a lot to this. So MnO4 minus aqueous. So that's what we've got. So those are our two half reactions. So we always start by dividing into half reactions, and then we're going to deal with them separately. All right. So let's take a look at this first one. So now what we're going to do is we're going to balance atoms, and then we're going to balance charge. So balance atoms and then charge. So there's a special way that we're going to do this. So let's start with our vanadium. So VO2 plus, by the way, you're just going to do this on one line. And I don't know why I made it hard for myself to do it this way, but there we go. So VO2 plus. So the first thing that we're going to do is we are going to do any non-oxygens and hydrogens. Non-oxygen and non-hydrogen. Well, I have vanadium. That's the only non-oxygen or hydrogen, and we're good. I've got one each, so we're good to go. Next, we're going to use water to balance the oxygen. I have two oxygens on this side. I have one oxygen on this side, meaning I need one more oxygen on this side. H2O. There we go. We're good to go. Oxygens are taken care of. So oxygen using water next. Okay, so non-oxygen, hydrogen, then hydrogen, and then charge. Okay, so I've just done oxygen. All right, next up, we're going to use, because we're an acidic solution, again, we're always going to do it in acidic, I'm going to use H+. I need two hydrogens on this side because I had water, which has two hydrogens. So two H+ on that side. Okay, good. Now that we have this balanced-ish, okay, so now that we have done all of the atoms, we're going to do charge next. What is the total charge of this side? What is the total charge of this side? So if we add this together, okay, I'm going to need a little more space on this side. If we add all of this together, I have a total charge on the left-hand side of +3, right? So +1 plus these two gives me a total of, this whole thing is +1. Each of those is +1, but two of them. So +3 is the total. Okay. The other side, I have a total charge of +2. So we need to reduce, because we're going to add only electrons. So that means one of the sides is going to go down. So how many electrons do I have to add? Right. So I'm going to say -1 to the total charge is going to give me +2. That means that I need to add one electron on that side. And now everything should be balanced. By minus, because charge is +3, but subtracting a number reduces the charge because I'm adding an electron. There we go. So that one is balanced. All right, next up, let's take a look at the manganese. MnO4 2 minus, arrow MnO4 minus. So balance non-oxygens and hydrogens. We're good to go. We actually have nothing to add to either side. So 1 manganese on both sides, perfect. Next, oxygen. We have 4 oxygens on each side. This one's easy. We don't actually have to add any water. And because we didn't add any water and it doesn't look like we have any hydrogen, we don't have to add any hydrogen. And so now let's do the total charge. So this side is -2. This side is -1. I need to subtract, I need 1 less charge on that side to get down to -2. That means my electron, I'm actually going to add 1 electron on that side. Good. All right. So adding, good. So we now have our balanced reactions. And so now if I rewrite the things that I have, so I had VO2 plus 2H plus an electron is in equilibrium with VO2 plus 1 water. Okay, and then I've got MnO4 minus yields MnO4 2 minus plus an electron. By the way, dead giveaway, if you have oxygens on the opposite sides, you're doing something right, or electrons on the opposite sides, you're doing something right. And so now we're going to multiply the half reactions. Well, what we're going to focus on is the electrons. I have 1 electron on this side, 1 electron on this side. I don't need to do anything. It's already balanced. So when I combine these together, and I'm just going to do it on this line instead, the electrons are going to cancel out, and I'm left with VO2 plus 2H plus MnO4 minus yields VO2 plus water plus MnO4 2 minus, all aqueous. Okay, good. And so now the last thing is we want to check and make sure that it is in fact balanced. It is in fact balanced. And so now here's the last part. So this, as acidic, what you have is, again, VO2 plus 2 hydrogens, 2H plus MnO4 2 minus yields VO2 plus water plus MnO4 minus. So this right here was my acidic balancing. So this right here is it being balanced, right? Everything worked out. This is acidic. Great. That's it. That's the end of it. If it asks for acidic balanced, there you go. That's it solved. Now this one right here, if I want to convert to basic, what I'm going to do is I'm going to say, all right, what am I not allowed to have? I am not allowed to have H plus, and you should only have it on one side. So if I'm not allowed to have that, what I'm going to do is there's 2 H plus that has to go away if it's basic. So I'm going to say, all right, well, I'll add 2 OH minus to that side, but it's an equality. If I do it to that side, I also have to do it to this side. So I'm going to add 2 OH plus to both sides, 2 OH minus to both sides. So these two combine together to give me what? Well, 2 H plus and OH minuses give me 2 waters, okay? And so now if I write it out, and I'm just doing this in extra steps and I shouldn't really need to, plus 2 waters that I just made, plus MnO4 2 minus yields VO2 plus 1 water plus MnO4 minus plus 2 hydroxides, OH minus. Well, at this point, we see I have 1 water on this side, and 1 of those waters is going to cancel. And so what I end up with is VO2 plus 1 plus a water plus MnO4 2 minus yields VO2 plus MnO4 minus plus the 2 hydroxides. This is my basic balancing. So it is now balanced as basic. That's it. That's how we convert to basic. So balance is acidic and then convert to basic if you need to. Okay. So balance this redox reaction. So again, give this a go, but I'm going to do it right now with you. And this one is a little bit more complicated, but not too much more. Yeah, here we go. All right. So I have 2 sides. I'll do one and then the other. So chromium Cr2O7 2 minus yields, I guess I'll just do the whole let's see. I don't know how much space I'm gonna need. So Cr, yeah, 3 plus. Okay. Okay. What's the first thing I do? I balance out the number of non-oxygens or hydrogens. So I need 2 chromiums total. Everyone good with that? All right. So next up, I have to balance the oxygens. I have 7 oxygen on this side. Therefore, I need to add 7 water molecules on that side. These are liquid, by the way, but I have to 7 water molecules on that side. Okay, oxygen is balanced. Next up, I have to add 14 H plus on this side, aqueous, because I have 7 times 2 hydrogens, so 14 hydrogens total. And now let's do charge. So what is the total charge on this side, and what is the total charge on this side? So 14 plus 14. So 14 plus minus the 2. So 14 plus minus the 2 gives me plus 12 on this side. And on the other side, I have 2 plus 3s, and that's it. So that gives me plus 6. Again, charge can only go down because we're adding electrons. So if I add 6 electrons to this side, the total charge is plus 6. So I'm going to add 6 electrons to this side. Boom. This is a balanced half reaction. Do I care if it's redox, reduction, or oxidation? No, I don't. Next up, let's take a look at the chlorine turning into chlorine gas. Okay, so in this case, again, I'm going to balance the 2 chlorines on that side, and that's it, because I don't have oxygen, I don't have hydrogen, and we're good to go. Again, it gets more and more complicated. We're going to work in some of these in class, but again, it's just the same concept. So total charge on this side is -2. Total charge on this side is 0, meaning the right-hand side needs to go down by 2 to give me -2. So plus 2 electrons. There we go. So now what I want to focus on, we're going to add these together, but in order to add them together, the electrons are going to need to cancel out. So I need 6 electrons in the bottom one. So I need to multiply the bottom by 6. Everything needs to be multiplied by 6. I'm sorry, not 6, by 3, because I'm going to double or triple the electrons. So I have 6 chlorines. I have 3 Cl2 gas, and I have 6 electrons. So now if I combine these things together, and I'm just going to rewrite the top thing, Cr2O7 2- plus the 14H plus 6 electrons yields 2 Cr3 plus 7 water molecules. Combining these things together, what do we get? Well, these 6 electrons and electrons should always cancel. And then we're just going to rewrite what we've got. 6 Cl minus plus Cr2O7 2- plus 14H plus yields 3 Cl2 gas plus 2 Cr3 plus the 7 water molecules and liquid. There we go. This is balanced. And again, we always start the balance with acidic. So this is acidic. So let's make it basic. I want to make it basic. I find my OHs, or I find my H pluses, and I add 14. I add that number of OHs to both sides. So this turns into 14 water molecules. These 14 water molecules are going to cancel all but 7 of those. And now I'm just going to rewrite the final thing. So 6 Cl minus plus Cr2O7 2- plus the 7 water molecules, liquid, yields 3 Cl2 gas plus 2 Cr3 plus 14 hydroxides. Boom, this thing is balanced as basic. That's it. That's how we do it. Every single time, that's the process that we go through. So solve this, balance this half using the half reaction method. We're going to do this in class. By the way, it says acidic, but do it basic as well. Same thing here, balance this. And that's it. We're going to talk about electrochemical cell in the next video.